Okay, so we're going to continue with what was in the lecture 8 packet, which was on organic chemistry, and then we will transition into lecture 9 stuff. So um, we were talking about the names of things, the carbon backbone, and the different kinds of functional groups, which are things added to hydrocarbons. And these kinds of functional groups that have a bunch of oxygen in them, especially, but also the ones with nitrogen, if you can, try to remember back to the things that they're analogous to, which are water and ammonia. And they have lone pairs of electrons, which act like Lewis bases. So that helps make organic matter soluble in water. Like most organic matter is not all that soluble in water. Think about like oil and vinegar salad dressing until you put what we call substitution. So we have these names for things dissolved in particulate organic carbon. Particulate is just a suspended carbon. Dissolved is truly dissolved. And both of them interact with the other stuff that's in solution. As I've mentioned a bunch of times, one thing they do is they help to solubilize the stuff in the middle of the periodic chart that is not soluble. They also contribute acidity to natural waters and to soils because they have these functional groups that include hydrogens, some of which are acidic. They include protons. So that's a thing. There's some other terms that I just thought I would mention to you now since I use them throughout the semester. So DOC, dissolved organic carbon, POC, particulate organic carbon. You also have DIC and PIC, which is dissolved and particulate inorganic carbon. Remember, the inorganic carbon is the stuff like carbonate, bicarbonate, CO2. Some people put methane in that same pool. Graphite and diamond. Those are the inorganic forms. We can also use the same convention for nitrogen and phosphorus, just sort of letting you know ahead of time. You will see people say DIP. It stands for dissolved inorganic phosphorus, or DIN, which is dissolved inorganic nitrogen. That would be, for instance, ammonium. POP is particulate organic phosphorus. So in these little acronyms, the D and the P are dissolved in particulate. The I and the O are inorganic and organic. And pretty much you only see them refer to these three chemicals: carbon, phosphorus, and nitrogen. Phosphorus and nitrogen because they're nutrients. Okay, so that brings up the next thing, which is natural organic matter. So if you think back to like the olden days of protochemistry, before we had all the sort of instrumentation that we have to identify things in very precise order with different spectroscopic and magnetic methods, people used to use kind of chemical methods. And the first organic matter that came on was stuff that was in soils, and through a series of kind of coarse chemical separation, people were able to determine that there's a variety of natural organic substances with a color gradient that goes from yellow to brown to black, and that there's a bunch of properties that vary with them. Now, this isn't a single chemical. It's what we call the humic substances. So you probably heard that term, soil humus. It comes from the same term. It's a category of substances, okay? What's interesting is when you take some soil and take out all the inorganic matter and just left with the humus, you can divide it into three categories based on how it behaves in water. So if some part of it dissolves in water, we call it fulvic acid. It's still not one chemical, it's a group of chemicals. If they're only soluble in really low pH, like less than pH 2, we call it humic acid. And if it's not soluble in any pH, we call it humin, okay? And there's some characteristics of these things, mostly the degree of substitution. This has the most substitution, this has the least, as well as a variation of molecular weight, lowest molecular weight, highest molecular weight. Some of the other characteristics are here. But the couple of things I want you to note is when you talk about organic matter and we talk about acidity, we're talking about functional groups losing hydrogen ions and then becoming negatively charged, which helps organic chemicals dissolve in water. It also helps them chelate metals. So this goes down, that acidity goes down as we go from this to this to this. And that's really just a measure of two things: the loss of a hydrogen ion and therefore the ability to chelate and dissolve. So again, this is a category of substances. This is some models. I've shown you this picture before. I haven't shown you this one. Model structure of humic acid. It just means humic acids, that general pool of stuff, can include a bunch of things in it, complex molecules with biological fragments that look like peptide fragments and sugar fragments. We can see some of those carboxylic acids I mentioned to you last time. These are the things that lose hydrogen. These benzene rings with double bonds on them, some of these hydroxides and ketones. And this is a fulvic acid. The two things that you can notice without knowing much organic chemistry is that this one looks bigger than this one, right? Heavier molecular weight. And if you were to count up the number of oxygens or nitrogens relative to carbon, in this molecule and this molecule, you'd see a higher ratio here. More substitution is what makes this soluble. In this one, only sparingly soluble. It's only sparingly soluble when you really crank on the pH, make it so low that all of these things lose their, let me say, instead of losing the hydrogen ion, they protonate, and you get some positive charges on this thing. And that will help it solubilize. And this is kind of what humic acid can look like. You can see it's got, this is a super high magnification image. It's got all sorts of surface area texture to it. And again, this is broad category of substances. So this is mixed material. It's not all just one chemical. But what's interesting is because this can disaggregate and make very, very fine particles that move around with the flow of the water, and other things can attach to it, becomes really important for things in aquatic and terrestrial ecosystems like soils, for things like micronutrients, the heavy metals, toxic metals, radionuclides, halogens, all those things are bound to it. And so it's really important to understand that it exists and what it does in the environment. Okay, so the next thing I want to talk about a little bit is what makes organic molecules soluble. Pure hydrocarbons are really low. Substitution of all those functional groups that we mentioned last time help make things dissolve. Specifically, if the functional group has oxygen, nitrogen, or sulfur, right? You can look where those all are on the periodic chart. They're really close to carbon. They make covalent bonds with carbon. They got extra electrons. They're Lewis bases. These guys help solubility. The other kind of thing that partitions into organic matter that doesn't help solubility are halogens. So these guys over here, fluorine, chlorine, bromine, when you add them to an organic molecule, they tend to make it less soluble in water. We're not going to talk about much. We talk about these a lot in the environmental geochem class. We'll talk about contaminants because a lot of contaminants have these on it. But most natural organic compounds that we find in the environment don't have a lot of halogen on them. So this is just something to know. So when you look at a molecule that's got something besides carbon and hydrogen, if there's a lot of these things in it, it's likely to be more water soluble. That's how I'd like you to think of it. Okay, so now we can look at, well, where do we find all the carbon? As you can imagine, most of the organic carbon in the environment is associated with biological activity. So what we call TOC, which is the total organic carbon, which is the sum of the DOC and the POC that dissolved in the particulate, that varies systematically in different places. We can find different proportions of dissolved to particulate, and this is largely a function of like the flow field. Right, if the water is moving really quickly and it's turbulent, for instance, we're going to have a much higher relative proportion of particulates. If we're in still water, like a lake, where the particulates can settle out, we're going to have a higher ratio of this. So for instance, in rivers, the ratio between dissolved and particulate can be like 1 to 100. So think about that. Only a tiny bit of the carbon that we find in most natural waters is dissolved. Most of it is the not dissolved one. Okay. And when we get to situations where we have higher particulates and higher flow rate, then we can get to higher, even higher proportions of particulate. It's also kind of interesting to note that in most natural waters, the DOC ratio to the total dissolved solids, which includes everything, all the inorganic salts and stuff, is about 1 to 20. Okay. And there are various natural and pollutant sources for organic carbon. We're not going to kind of belabor the pollution stuff too much, but safe to say that anything that enhances biological activity, fertilization, agricultural runoff, you put a little miracle grow in your yard and it runs off, whatever, anything that produces extra biological activity in an environment is a pollutant source of organic matter, wastewater from your toilet, et cetera, and that goes into the environment. So this are a couple of plots from White, kind of showing you two things. The first one is the total organic carbon in milligrams per liter with sort of two bars. The red is dissolved and the black is particulate. And then this is kind of a breakdown of the kinds of substances that you see. The humic substances, which we've mentioned, and simpler compounds like individual disaggregated carbohydrates or amino acids or hydrocarbons. And you can see the solubility here, kind of, or the concentration that you find in the environment sort of follows. Hydrocarbons are low solubility, so don't have very much of them. Carbohydrates tend to have the higher solubility, much higher proportion of oxygen to carbon, so they are soluble. And up here, some of these terms we'll talk a little bit more about, but you can see seawater, groundwater, and rain very, very low. What is an oligotrophic lake and a eutrophic lake? An oligotrophic lake is a lake where the solubility of oxygen is controlled primarily by exchange with the atmosphere because it's got low biological activity. We'll talk about this in more detail coming up, but it's a low biology lake, and a eutrophic lake is a high biology lake, high enough that we get to a circumstance where the water starts to change characteristics very greatly between the shallow and the deep water, very nutrient rich. It supports very high biological activity, almost as high as you find in a marsh or a bog. And so we'll talk about those environments more later, but you can see that the proportion of dissolved particulate looks kind of similar in all of those. So both types of organic matter, particulate and dissolved, can help interact with solids in the environment. And our topic that we're going to get onto next has to do with weathering and clay formation. And this is a place where organic matter is really important. It can bind to those surfaces and help break apart silicate minerals and other inorganic minerals. It can also contribute acidity, which helps dissolve minerals. And so we tend to find the rate of dissolution of inorganic particles in the environment increase in the presence of organic matter, right? And you can find this examples here in Hawaii where you go between the wet and the dry sides of the islands and you look at lava flows of similar ages. And because we're on the wet side, we tend to have greater, biological activity, and we'll see much greater rate of breakdown of lava than we will see in the dry environments. So this is an example of a bunch of different simple minerals, okay? Calcite, calcium carbonate, dolomite, calcium magnesium carbonate, hematite is iron oxide, pyrite is iron sulfide, galena and gold, galena is a lead sulfide. And so you can see here the change between just dissolving it in water, it's in equilibrium with CO2, so like a little bit acidic, versus dissolving it in water with humic acid. Look at the ratio of how much it goes up, right? So calcite increases its amount of solubility from 0.65 to 17.4. The organic matter really helps solubilize stuff. And it does it in several different ways. It can bind ions by chelation to help lower their activity in solution, which promotes additional dissolution. They can attach to mineral surfaces and help with electron transfer. And these are just some examples. This is a chelate of copper by this carboxylic acid and this hydroxyl group on this benzene ring. You see both of these things are going to donate electrons to this copper. That's what makes it a chelate, right? It's a complex, but it's a bidentate ligand. So that's, for instance, a way of helping to solubilize copper. And interestingly enough, this organic matter can attach to ions in solution, but can also attach to surfaces. So this is meant to be like a depiction of a clay mineral, which has got aluminum hydroxide layers, as we'll talk about later today. And this carboxylic acid anion, so lost this hydrogen ion, can connect to this hydrogen. And after it binds there, it can help to promote the exchange of electrons, which will disaggregate this aluminosilicate mineral. So one point I just kind of want to make out about chelates is that both POC and DOC will chelate metals. When you're a metal and you're just looking for a loose base to help stabilize your positive charge, you don't really care if that is connected to a particle or something that's dissolved, right? As long as the water's flowing and the DOC to POC ratio is constant, that also doesn't matter. But we get into situations where the flow field changes and sediments come out. So think about rivers flowing into the ocean or flowing into an estuary, or rivers flowing into a lake, or what happens in a sewage treatment plant when a heavily laden particle stream goes into a settling basin. In all these cases, when we settle out particles, the stuff that is complex on the POC settles out. And so sometimes, and in some environments, we'll find really, really organic and heavy metal rich sediments because the flow field of the water changed and the things that were complex by particulates settle out. And so this is one of the reasons why sediments that we find in rivers near the mouths of the ocean, whether there's an estuary proper or not, or whether there's a harbor there, those sediments tend to have very high heavy metal concentrations. And they tend to be places where we can bioaccumulate into food chains heavy metals, even in a natural sense, even without contamination in the environment, very high concentrations of metals that were associated with the particular organic carbon that get settled out into the sediments. So just kind of want to reinforce this. When an ion is complex by DOC, it's literally dissolved. And when an ion is complex by POC, it is only suspended in the water. Okay, so there's tons of different natural ligands, right? And many of them are based on functional groups with oxygen, especially hydroxyls and carboxylic acids and ether, but there are also nitrogen-bearing functional groups that are really important. And different specific ions can have different specific reactivities for different types of organic matter, different chemicals within the fulvic acid pool. It starts to get pretty complicated when you start to kind of deconvolve what metal is doing what with what compound. And I don't want to kind of go into this in a great amount of detail because I think it'll be kind of overwhelming, but I kind of want you to think about this as overall a mechanism of having increasing organic matter, which is a biological phenomenon primarily, increases the solubility of a lot of sparingly soluble metals, as we've already talked about. There are also lots of pollutive ligands that can be introduced into water. Some cases so strong of chelating agents that they can suck metals out of pipes, right? And again, Mariah really talked about, we're talking about them in the environmental chemistry class, but I'm not going to focus on them here, but these relationships can be really, really strong. And part of it is related to the acidity of these functional groups. So the easiest one to understand are carboxylic acids, which is, you recall, we write them as RCOOH. I just pulled out the OH to help show it to you. It's acidic because this hydrogen can come off and it can make a carboxylic acid anion, the conjugate base, and a hydrogen. And these things are really good at chelating metals. So just like our relationship between pKa and pKh, which we've talked about before, you can apply it here to show, we know that the pKa, the minus log of the acid dissociation constant, is just the minus log of the conjugate base to acid ratio plus the pH. And when this ratio goes to 1, the log of 1 is 0. So we're in a situation where pKa equals pH. This is why I was showing you those germ plots last week of acetic acid, which is one of these kinds of carboxylic acid. So whatever the pKa of an acid is, and you can look this up in a table, you know that if the water is at that pH, it's going to have an equal ratio of these things. And what's even better is that you can calculate for a water that's 10 times more acidic than that, right? If the pH is 1 unit lower than pKa, this ratio will go down to be 0.1. If the water is 1 unit of pH more basic than the pKa, it will go up to a ratio here of 10. So you can kind of see what the ratio of conjugate base to acid is. And from the perspective of organic matter chelating metals, we want to find acids that have a pKa that is low enough, right, that the conjugate base to acid ratio remains high even at low pH. So if we're at the pH of, in the 4s around the endpoint of CO2, we have a carboxylic acid with a pKa around there that even at that pH is going to be a lot of this stuff and not that much of this stuff. Whereas an acid with a pKa of 8, when we're down at a pH of 4, this ratio is going to be 10 to the minus 4, and it's not going to be much conjugate base present. So for instance, for an acid with a pKa of 8, in pH of 8, like seawater, we would find a ratio of acid conjugate base acid 1. If we lower the pH by 1 unit, it becomes 0.1. If we lower the pH by 2 units, it becomes 0.01. So if we look at acetic acid, which is the simplest carboxylic acid other than formic acid, which has a hydrogen here instead of a methyl group. That's the stuff that ants put down at their trails. It's kind of a special case. But acetic acid has a pKa of 4.8. What does that mean? That means the minus log of the acid dissociation constant is 4.8. The acid dissociation constant is 10 to the minus 4.8. Okay, and this is close enough to this lower endpoint of CO2 that when we stick this carboxylic acid in water, almost all of it is dissociated. Almost all of it is in the conjugate base form. Okay. You have to go down to really low pH. You'd have to go down to a pH, like for instance, if we went down to a pH of 2.8, which is pretty low, then our ratio of conjugate base to acid would be 1/100, because it jumps 2 steps down. And many other carboxylic acids behave like acetic acid, right? And this is just to remind you of the lower endpoint of CO2. That means that they are dissociated when they're in water, okay? And a carboxylic acid will be more acidic than acetic acid. If there's anything in that carboxylic acid that is electronegative, that like wants to pull electrons, that helps stabilize the negative charge on the carboxylic acid. And anything in that carboxylic acid that's a little bit more electropositive, like not liking of electrons, will destabilize the acid and make its pKa a little bit higher. And I have a table in here with a bunch of examples that I'm not going to kind of walk through because it's fine print, but it basically shows you, for instance, if you take acetic acid and you replace all 3 hydrogens with 3 fluorines, fluorine being the most electronegative element, you can see that the pKa changes by 5 orders of magnitude. That stuff is super acidic because you're putting all those fluorines on there and they're like sucking electrons to them. And you can go through this list, like for instance, you can take a molecule where, you know, we've got here's with 3 chlorines, here's with 2 chlorines and 1 hydrogen, there's 1 fluorine and 2 hydrogens. So you can see that the less halogen, the less difference it is from acetic acid. Those are just simple cases. Here's another really simple case. This is called benzoic, actually butyric acid, because it's got 4 butyl, 4 carbons in it. And you can put a chlorine in several different places. You can put it next to the carboxylic acid, 1 carbon away, 2 carbons away, and you can see the relative effect. When this chlorine is all the way at the other end of the molecule, the pK isn't all that different from acetic acid, right? It's like a little bit different. So this is kind of how, and I don't expect you to be able to look at organic molecules and figure out how their pKa varies relative to acetic acid, but you will see that a lot of natural acids do have pKa's in that range, especially a lot of the ones on this part of the table. And then some other molecules with higher pKa's, right? Alcohols, right? And some of these nitrogen-bearing compounds, and various other kinds of alcohols with really low pKa's. These molecules won't be ionized. They won't lose those hydrogens because the pKa is too high. High pKa means a low acid dissociation constant. Okay, so not everything ionizes, and this is part of why when we look at fulvic acid and humic acid, the difference between them is that it's not just the amount of functional groups that are in there, it's the amount of functional groups of the form COOH, which is the kind that really dissociates. Okay, so one of the things to point out about organic matter, when you stick it in water and some part of it dissolves, the vast majority of it dissolves as an anion, a negatively charged thing, right? Some of it is positive, but not very much. So that means that if we have to maintain charge neutrality in our solution, it has to take up some of the minus charge. Now, if we look at the inorganic ions, the things that are not related to organic matter, if we go into an environment where there's not much organic matter, we're going to, if we sum up all the cations and all the inorganic anions, we'll find them to be roughly equal. But if we go into an environment with a lot of organic matter in it, there's going to be more cations than inorganic anions because the organic anions are making up some of that pool. And so one of the sort of simple ways to assess how much organic matter is in the water is to measure the ratio of inorganic anions to cations. And the lower this ratio goes, the more organic anions must be making up the difference. Okay, so that's the intro to organic chemistry. Are there any questions about that? All right. So now we're going to move on to the next topic, which is weathering. So there's some new reading. And you'll see that in chapter 6, we're going 249 to the end. And some of the content we're going to talk about this time is in the pages right before this, like 238 or so to 249, the clay mineral structure. And then we got a little bit of chapter 13, 7 pages in there. Okay. So, you know, look at these things this week. And if you haven't done your chapter 6 reading, the part of before this, please do that too. So we just finished this. So now the rest of the time today and next time, we're going to talk about weathering, secondary minerals, surface reactions, and then next time we'll talk about soils and soil formation in relationship to this. So weathering is a broad topic, and it's important in geochemical cycles. It's important for looking at how rocks transform in the environment. It's important for looking at the development of soils. It's important for understanding the way water in the hydrologic cycle changes composition as it interacts with rocks. It's important from a geological perspective to look at how the conditions of weathering may have varied over time. Like think back to an early proto-Earth where we didn't have biological activity. So we're not gonna have the organic acids, we're not gonna have the chelating effect, we don't have oxygen in the water. Weathering was really different back in the earliest days of the planet. So this is just some of the ways that weathering interacts other things besides that, right? So obviously the rock cycle, ecosystem sustenance, composition of the oceans, composition of the atmosphere. So it turns out that the weathering of silicate rock is the primary control of CO2 in our atmosphere. Really slow, right? CO2 is not going to get us out of greenhouse warming or anything like that. But one of the reasons why Venus has all its carbon dioxide in the atmosphere and Earth has most of its carbon stored in rocks is because of weathering and the making of carbonate minerals, the presence of water, the hydrologic cycle, the plate tectonic system that allows us to recycle material back in the metal. There's several differences between us and Venus, but there's a very clear link to what is in our atmosphere because of the weathering of rock. And so it's one of the things that sometimes people don't associate with weather. So weathering has a bunch of different causes, right? There's kind of physical causes of it, there's chemical causes, there's biological causes, and especially in the case of chemical and biological. So physical weathering, you know, can involve wind and very dry environments. But chemical and biological weathering are almost always mediated by water. And so if there's water present, water is going to dissolve ions, it's going to carry stuff along. And that means that we get new solid materials being formed by the interaction with the water, and we get dissolution of stuff. This through-flowing water is changed in composition. And this is just to remind you of some of the different kinds of weathering that you can see that are all chemical in nature. So, you know, we look at just weathering in the most broadest sense. It varies as a function of things like temperature, right? The rates of a lot of the breakdown reactions for rocks go way up when the temperature goes up, and they go way down when the temperature goes down. Present or absence of water, biome factors, how many organisms are living in an environment, how much organic matter are they producing. And then in addition, when we're in a terrestrial ecosystem and weathering is resulting in the formation of soil, we also want to know, well, what is the rock made of, right? It's going to weather, okay, but what's it going to weather into? Well, it depends on what the rock is. There are physical factors of the rock, like how porous is the rock? How easy is it for water to flow through? How fractured is it? How textured is it? Does the rock have big honking mineral grains that are welded together very strongly? Or do the mineral grains have big surface area and pukas around? there's what are the minerals in the rock? How soluble are those minerals? And go back to our discussion that we had last week about mineral solubility. And I'll just say that, like a lot of the other topics that we discussed in this class, soils are also susceptible to many anthropogenic factors. Just think about acid rain, which is something I'm sure you've all heard of. That addition of inorganic strong acid to soils and environments receiving acid rain contributes to increases in the rate of weathering of many orders of magnitude, plus leaching of metals out of the soil and stuff. And so these things happen. Sometimes they're hard to disentangle from the natural phenomena because it happens so much nowadays. But in any event, we're not going to focus on the human perturbation aspects. So we can say, well, how do we know what minerals in a rock are formed by primary processes, meaning the original formation of the rock, versus secondary processes, which are typically weathering and disaggregation? The way we do that is by looking at the relationships between the different minerals in a thermodynamic and a solubility sense, see if they're stable together or not. If you have a rock with an assemblage of minerals that are just thermodynamically not stable next to each other, then we know that that is an aggregate. Somehow it's put together of weathering products and non-weathering products. You can also think about the compositions of the water, and in cases where we still have the water, like the groundwater setting, we can look and see what changes we're seeing along the flow path in groundwater and what changes we expect from different mineral solubility reactions. We can oftentimes predict what kinds of rocks are in the subsurface on the basis of how we're seeing the water chemistry change as we go down a flow. So, just to kind of bring home again, there's a temperature effect for sure for solubility. It's also a pressure effect, and this doesn't really affect us like here at the surface of the earth. If you go down into the oceans and you look at how does rock weather, 6 kilometers water depth is going to be different than it weathers up here at the surface because there are pressure effects on some of the mineral solubilities. There's also effects of what's in the water that's doing the breaking down of the rock, if it's the kind of weathering that involves water. So there's a lot involved. There are actually programs that you can get that help you calculate things like assemblages of minerals and water compositions and temperatures for conditions where you only know some of those things. One common program people use is called PHREQ, P-H-R-E-E-Q. It's an open source thing developed by the USGS like 20 years ago. And you can find freaks. That's what the people who use it online communities, that go into gory detail about how to maximize that program. And basically what it has behind it is just a whole bunch of mineral solubility diagrams, redox relationships, and the like of the kind that we're talking about in this class. So here's some other additional factors, just to kind of reinforce that, again, the rock type that we have, the temperature, the pressure, the composition of water, the amount of organic matter, and the pH. These are all kind of important variables that affect how alteration is going to happen. So having said all that, we're now just going to look at alteration in a very general sense and not look too much at how these variables matter. I just want to emphasize that it does matter. It doesn't matter where you are, what your rock is made of, et cetera, et cetera. So the first place to start is the Bowen's reaction series. Does everyone know what the Bowen reaction series is? Does anyone not know? Okay, Bowen was a famous, I guess you would call it geologist, mineralogist, petrologist from the turn of the prior century, meaning like the early 1900s, who hypothesized that in a magma that starts out with a high temperature, high magnesium and iron, what we call mafic composition, if you just cool it and keep it all together in one pile and crystals start to settle out, that the composition of crystals are going to change over time as the magma cools. The magma composition will change and the crystals coming out will change. It's called the Bowen's reaction series. And there's two sides to it. There are the aluminosilicate minerals like olivine, pyroxenes, amphiboles, biotites. And then there are the feldspars. Anorthite to albite, which is the calcium-rich to sodium-rich feldspar, and then progressing into potassium feldspars. Both of them end up with these chemicals like minerals like quartz, which are basically very low in things other than silicon. Okay, this is like a super oversimplification. We don't believe in this in igneous petrology anymore. We don't believe that there's any place on Earth where we can find this sequence happening in a large scale, right? It was proposed, it was a cool idea in the early days, and there's components of it that make sense because there's a pressure temperature stability for these minerals. It's just that natural magnetic systems are more complicated than this kind of typical closed system that he had assumed for the reaction series. This is something that you learn in like Earth Sciences 101. However, it is useful in a different way, which is that Bowen's reaction series helps us understand the susceptibility of minerals to alteration at the surface of the Earth. Because it turns out that these high temperature minerals, having formed at relatively high temperature, are more susceptible to alteration than these low temperature minerals that form at the end of the sequence. There's also a change in the oxidation state. Like when we drag magmas from the interior of the Earth, and we'll talk about this in our third unit, they start out with iron 2 because the environment there is reducing. Iron 2 is not stable at the surface of the Earth. It wants to oxidize to iron 3. And so any one of these minerals that has a high amount of iron in them, in addition to the temperature effect of Bowen's reaction series, the implied effect of going from more reduced to less reduced also makes the minerals more unstable for weathering to less unstable. So we can look at Bowen's reaction series as a kind of index of how susceptible a mineral is to weathering. So if you imagine a basalt, like here in Hawaii, it doesn't have any quartz in it. It doesn't have any of these minerals down here, in fact. But if we were to weather it in, in the environment, all these minerals are going to go away and they're going to react to, as we'll learn, clay minerals. If we went to a place where, so there are some places where you can find quartz normative basalt, such as Iceland, where you can find little bits of quartz in it. What you would imply is that as you're breaking down the rock, those minerals that are the least susceptible to weathering would be the least likely to break down. So the weathering product that you get, the soil, for instance, or the soil, is going to be enriched in those grains that don't like to break down. So this is from another geochem textbook that's now out of print that looks at this from a slightly different perspective. This is like a very gross overall perspective of if we take a rock and we break it down in the presence of water and we allow that water to kind of flow through, what happens? We call the process chemical fractionation. We separate the chemical elements from each other. So on this side of this diagram, you can see here, sodium, potassium, magnesium, calcium, those are the most soluble elements. They dissolve, they get sucked into the water and they transport through. Eventually they're going to make it into the ocean. And that's why we have so much of that stuff in the ocean. Or here, the elements that are resistant, that are part of those minerals like quartz, down here near the bottom of this series, they don't really like to dissolve. So they build up in the soil. They don't move very far. So this can, you can think about this as like, if we've got a piece of rock, we're running water through it, how far do the things that we dissolve move, right? Not very much to very much. How soluble are they in water? Not very much to very much. What builds up in the solids in the weathering zone? Very much, not very much, right? Because of the water effect. Now, what's interesting to me are the ones in the middle, right? Because the ones in the middle are super sensitive to conditions like how much organic matter is present and what is the PE, right? So iron can change how soluble it is or it isn't dramatically as a function of do we have organic matter or not. And we're going to see when we talk about soils next time, as we go down from topsoil down into lower horizons in the soil, the amount of organic matter goes way down. So the iron can be soluble up near the top and insoluble near the bottom. And we can actually find horizons where the iron changes from soluble to insoluble, and it gives us kind of like an orange stained zone. And there are other elements in this category as well. And then we have these elements here, aluminum, silicon, and potassium. It says here hydrolysates and clay minerals, and we'll talk about what those are in a second. These are things that can reluctantly be made to go into water, not very easily, but at least to the extent that as we start to break down materials, for instance, in a vertical column, like we find in soils, we can start to see a separation between layers that are rich in this stuff and layers that are rich in this. And we'll talk about this in more detail. We can also see carbonate minerals in here. Some fractions of calcium and magnesium are not 100% soluble. If we get into a situation where we have a lot of dissolved carbon in water and the pH isn't too low, then these things come out, they precipitate out. And so we find this here in Hawaii, for instance. They call them caliche horizons. They're little sort of layers of white stuff that we find in the soil. If you go to really dry areas like along the Waianae coast, or some of the islands that are in the shadows of other islands like Lanai, you will find a lot of calcium carbonate and sediment. You know, a big rain comes through, some of it may redissolve again, but some fraction of it doesn't. And people have actually used the presence or absence of caliche in paleo soils going all the way back into the earliest part of Earth history to kind of look at, for instance, well, how much CO2 did we have in the atmosphere, and how may that have changed and affected the availability of carbon to make these? What was the pH in the environment like? And how much respiration? So think about photosynthesis and respiration. Respiration is what we do. There's other organisms in soil, for instance, that are respiring organic matter, producing carbon in situ. And that carbonate, or that CO2 that dissolves in water to make carbonate, can help to make caliche or calcium carbonate. Okay, so this top plot is a table of primary minerals, same things as you'll find in that Bowen's reaction series 2 slides back, and the clays that come from them. And I don't want you to memorize names. What I want you to see is that clays are a whole category of molecules, we'll talk about how they're formed in a second, that can interchange with each other by how much hydrogen and potassium and magnesium and iron they exchange in calcium. So they're a family of minerals with a couple of structural similarities, and the composition of the through flowing mediating water can transform one kind of clay to another clay. And as we migrate along this diagram, okay, we go from clays that have a lot of metals in them besides aluminum and silicon to clays with less. So all the way over here we're at kaolin, which is kind of an agricultural term for kaolinite rich soils, which kaolinite is an aluminosilicate clay that has very little other substitution into it, very little other metal in it. So this is like a sequence of no weathering, some weathering, more weathering, a lot of weathering. And if we find a lot of kaolin or kaolinite, like we do in tropical weathering environments like here in Hawaii, we know that the rock that it came from has been heavily weathered. We can go to other places where the temperature is colder and the environment is drier, and instead we find these kinds of clays, more complicated names and minerals. Vermiculite, that's the stuff they put in potting soil. There's a reason why we care about this extent of weathering, because these clays, by having all these other metals in there, get a very open structure that allows them to take charges on their surfaces that allow them to interact with solutions and hold other ions onto them by something called cation exchange. So we see that here, there's a thing called layer charge. Okay, the layer charge, and we'll talk about where this comes from in a moment, but it's basically the number of excess charges on the surfaces of the clay layer as a function of how much substitution they have in them. And you can see that they're variable, but this kaolinite, which is all the way over here, has very little, right? So weathering overall reduces a clay mineral's ability to hold other stuff to its surface. And this is one of the primary functions of clay minerals, is holding other things onto their surfaces and soils to make them bioavailable, as we'll see in a second. Okay, so for instance, if you just take the same rock and you put it in different environments with different amounts of rainfall, okay, and you look at the weight percent of 3 kinds of minerals in the solid. Smectite, which is one of these just barely altered clay minerals, is up here in this, excuse me, it's in this category up in here. It's not named specifically, but it's, you know, smectite is somewhere in between vermiculite and montmorillonite. There's a lot of names. But anyway, it's a highly substituted clay. kaolinite, the one that's not very substitute. And if you crank on kaolinite enough, this is just aluminum, silicon, oxygen, hydroxide. You can make it into bauxite, which is just aluminum hydroxide. Bauxite is the rock deposit name. The mineral is called gibbsite. So if you hit it with enough water, you can even dissolve out some of the silicon and leave behind an aluminum-rich residue. And this is just, in this case, as a function of rainfall. Same rock, more weathering, you get different weathering products. Okay, so this is the structure of gibbsite. It's aluminum with hydroxides around them in an octahedron. An octahedron is an 8-faced thing with 6 dots on it. It's like 2 square pyramids stuck together. And you can see here that each one of these oxygens is shared between 2 aluminum. It's a sheet, okay? And this is a very structured thing. In gibbsite, we don't find gibbsite or it's in the rocks called bauxite all that often. We find it in some environments, but it's not super common. But we're going to see in a second, it's really important as one of the 2 principal layers in clay minerals. So we don't have any clay minerals up here yet. But I just want you to compare how structured this looks to something that's very unstructured. This is goethite. It's a type of iron oxyhydroxide. And there's a whole category of these things. These are very open structures. Most of the iron that we find, the iron 3, is in this form. Very little of it is dissolved, as we've talked about before, especially when there's no organic matter. But it can make these very small amorphous grains of goethite, which can still interact with solutions because they can take charges on them. And we'll get to the charges in a moment. Okay, so then we get to clay minerals. So clay minerals are basically taking a layer like gibbsite, right? Like this stuff here on the right, and linking it up with another layer called the tetrahedral layer. The tetrahedral layer is made of tetrahedrons of silicon. Silicon with 4 oxygens around them. Just like most silicate minerals are based on silica tetrahedra. And the way these things combine together, and I have some better diagrams coming up, as you can, well, so I'm going to wait to describe the details of how they bind together. But you can take in a clay mineral one of these octahedral layers made of aluminum, and one of these tetrahedral layers, and you can make what's called a TO clay. It's got 1 tetrahedral layer, 1 octahedral layer. Or you can make what's called a TOT, like an Oreo cookie, where it's got 2 tetrahedral layers. Okay, and these clays form in slightly different environments. And they have slightly different characteristics. But what we will find is that these red layers transmit surface charges because they're on the outside of these stacks. And the amount of charge they have causes successive sheets of these things to expand or contract. Think about vermiculite, how open and expanded it looks. And so the density of charge allows bigger ions to stick in there. When it's real high density of charge, things can separate out a lot. We could put a complex ion in there like ammonia. It can also hold other particles to their surfaces. And like I said, we'll get to the details of those in a second. But I also want to point out that you can also have clays where the octahedral layer is made out of something other than aluminum. It's magnesium oxide. We call them brucite layers. You find them in rocks that have very high magnesium concentrations. They're much less common, so I'm not going to talk about them too much, but you can see it referred to here. So some clay minerals, instead of having aluminum and silicon, they have magnesium and silicon. Okay. Another thing I like to point out to people is that the proportion of aluminum to silicon changes between TO and TOT clays, right? In a TOT clay, we have twice as much silicon as in a TO clay because we've got 2 of those layers per layer of aluminum. So you can usually tell from a chemical formula if it's a 3-layer or a 2-layer clay based on the ratio of aluminum to silicon. Here it's 1 aluminum to 2 silicons. There it's 1 aluminum to 1 silicon. Okay, so now this is how those sheets go together. These are the octahedrons of aluminum hydroxide kind of sitting on their side and how they share electrons. This is how the tetrahedral sheets of the silicons look. The silicons, the orange dots, 4 oxygens around them. And so to make a sheet of tetrahedra, this basal layer is completely shared, right, between neighboring silicons. Then you got these dudes poking up. When they combine together to make a clay, these poking up guys insert themselves up into this layer, and that's what makes the TO clay. And it can happen twice. You can get another layer coming from above to make a 3-layer clay, a TOT clay. And again, the details of this structure isn't that important. I just thought, if you wanted to visualize it, you could. And this is just a little bit more business about the ratios of of silicon to aluminum. So the simplest TO clay we know of, 2-layer clay, is kaolinite. That stuff I just said was really super weathered. This is what it looks like. It can look in all sorts of different ways. It's typically very pale, very chalky, very finely grained. And it's got this formula of Al2Si2O5OH4. That just comes from the TO, whatever proportions from those ratios on the last slide. And you can see here we got, ratio of 1 to 1, as we would expect. 1 tetrahedral layer, 1 octahedral layer. The simplest TOT or 3-layer clay is this chemical here. It's called terephthalate. And you can see here, the main distinction of it is it's got twice as much silicon as aluminum, right? So it's got 2 of those tetrahedral layers. Okay. So we'll come back to clays in a second and how they can affect composition. I just want to take a step back and remind you or introduce you, depending on whatever the case is, of the 3 main ways that solids can interact with water in a chemical non-stoichiometric sense, right? Remember, non-stoichiometric means there isn't a simple molar proportion ratio between the 2 reactants and the products. And those are adsorption, absorption, and ion exchange. So adsorption, we've talked about a lot, right? This is like, for instance, Lewis acid, Lewis base interactions on the surface of a particle where something is being held by an ionic relationship or a sharing of electrons relationship. Absorption, the difference is just the 1 letter here, is a chemical incorporation, like some chemical A is floating around in solution. It sees a particle, reacts with it, it becomes part of the particle. This tends to be a lot less reversible than this. And then we have what we call ion exchange, which is also another way of thinking ion swapping. So we have some ions that are associated with particles that will liberate themselves into solution, while other ions in solution will then associate themselves with the particles. So we get a population of ions that if we were to dry the water out and filter out those particles, those ions would be stuck in the particle. Okay, and this thing happens all the time as part of water purification systems. It happens all the time in nature. And we're going to talk about a specific kind of ion exchange that happens on the surface of clays due to all that layer charge and substitution that I alluded to a couple of slides ago, because this ends up being a really important attribute of clay minerals that affects many different aspects of the weathering regime and how weathered materials interact with the ecosystem. Okay, so in a most general sense, there are 3 ways that particles can acquire charge, right? So this is slightly different than this. That's how solids interact with solutes. This is how do solids themselves charge up, and how does this affect weathering regime, composition of through-flowing water, and the distribution of chemicals between solutes and particles. And we're going to see how these 2 things work together in a second. But the main way that particles get charges on them is acid-base. Just changing the hydrogen ions and hydroxide ions with the solution. Ion exchange, the last thing on the list down below, is another way that particles can get charge. And then charge transfer interactions, the sort of Lewis acid, Lewis base, is another category. So I want to look at each one of these 3 things now in order. Okay, so acid base. I've shown you this diagram once before. It may seem a little bit cryptic, but if we have a particle a solid, and that's what this kind of hatched line thing here is. And it's got OH in it, right? And now I want you to think back to clay minerals, right? These sheets have OHs on them, okay? We can go all the way back to gibbsite to convince ourselves of that. Each one of these little bigger balls is an OH, okay? So if this is a gibbsite sheet and it's part of a clay mineral, that clay mineral has OHs and on it, some of them can be on the surface. So it turns out that those OHs and OHs that we find in other things like organic matter or other minerals besides aluminosilicate clays can interact with the solution to either lose a hydrogen ion, like act like an acid, or gain a hydrogen ion, meaning act like a base. The difference is that when that happens on a particle, the particle gets a charge, right? If this particle has a bunch of OHs on it that are acidic and it loses them, the particle takes a negative charge on its surface. And all of a sudden it's going to be like, oh, I'm a negative charge. I want to stabilize that, and it's going to suck some cations from solution onto its surface. And that is the gist of a lot of ionic interaction between particles and solutions. So if you think back to this thing, this table here, where was it? I'm trying to remember where the table was. Down here, where I said layer charge. That is basically a measure of the amount of acid-base chemistry happening on the surface of the particles, creating charges. And in the case of clay minerals, the charge is almost always negative, which gives us to something we call the cation exchange capacity, which is that the bigger the negative charge on a clay, the more cations it can hold onto its surface. Just imagine you're a clay mineral, you're sitting there in some soil, and you got plants growing on it, and the plants are looking for potassium, they're looking for ammonium from the soil as nutrients. If the clay minerals can hold a lot of that stuff on their surfaces through cation exchange, that makes that soil really fertile. If the soil is made out of super weathered grains like kaolin, which have a really low layer charge, then they can't hold that stuff. That stuff just washes through with the water. So the amount of substitution on the clay and the layer charge, which is a function of this acid-base chemistry, really affects how fertile a soil is going to be. So this is how these things, are related together. So this can happen whether the particle surface is made up with silicon or aluminum. That's the two examples here, or organic matter. And the key point I want you to recognize is that just like any other acid, there's a specific pKa of solution where this reaction is going to happen or that reaction is going to happen for that particular particle type. And so what we find is a lot of particles in the environment will take either a negative or a positive charge depending on the pH we stick them into, right? So if we stick a particle into a low pH environment, it's going to do this, and it's going to take a positive charge on its surface. If we stick it into a high pH environment, it's going to lose its hydrogen ion, and then we're going to get a negative charge. Now there's other categories of particles that regardless of what pH we stick them into, they're either going to be all positive or all minus, and we'll talk about those in a second. But this genesis of charge on particles is critically important for the kind of progress of weathering and the composition of the water. Just kind of want to show you, for instance, how does charge develop on a really simple particle? So this is manganese oxide, manganese +4 oxide, not soluble in water. But you can see here that in a series of steps, the first thing that happens is some of these terminal oxygens, they hydrate. They react with water. And then depending on the how acid or base the water is, if it's a low pH situation, we can gain hydrogen ions onto some of these other hydroxyls, and that gives this particle of manganese a plus charge. Or if it's a really basic situation, then we can lose one of these hydrogens from this water and get an OH minus. And so this generates a negative charge, this generates a positive charge. In reality, in real particles, we can find both of the things happen, right? So you can find natural particles that have some negatives and some positive charges. They're heterogeneously composed, and I don't want to give you the impression that it's like an either or kind of situation, but these are the kind of simple mechanisms through which the charges develop. So basically, this is kind of showing you an example for an SiO, right? A silicon bonded to an oxygen at the end of a tetrahedral, a tetrahedron in any mineral, whether it's a clay mineral or any other silicate mineral, can at low enough pH accept the hydrogen ion and take an extra hydrogen onto that oxygen and give it a positive charge. And at high enough pH, it can lose a hydrogen and make it minus charged particles. Okay, so that brings up the idea of something called the isoelectric point, sometimes also called the 0 point of charge, or ZPC. And I apologize if you've noticed that there's a lot of acronyms in geochemistry. It's true, there are a lot of acronyms. I always try to define them, but if anything is ever confusing, please, ask. The interesting thing about the 0 point of charge, or the isoelectric point, is it is the specific pH for any specific mineral where the sum of all the charges from acid-base chemistry on the surface are 0. Doesn't mean there's no charge. You can still have some pluses charges and some minus charges, but when you add them up, it's 0. And there's only one pH for every mineral where that happens. And if you can imagine, if the pH is at the 0 point of charge and then we lower the pH somehow, then we're going to protonate those acids and make a positively charged particle. And if we raise the pH, a great way to raise the pH is to take particles in a river and stick them in the ocean, right? And the pH usually jumps up by over 1 pH unit when we go from fresh water into the saltwater part of the hydrologic cycle. Then we're going to, if we're near the 0 point of charge and we go to a more basic situation, we're going to go from a neutral charge to a minus charge. That's how 0 point of charge works. Okay, because it's a pH where the charges are balanced. And the charges are mostly from acid base. So here's a couple of tables kind of showing you what the pH of the isoelectric point is, or the pH of the 0 point of charge. So you can see, for instance, all these minerals up here, which are all silicate minerals plus this manganese oxide, they have really low 0 point charges or isoelectric points. That means that pretty much regardless of how acid or base the water is in the natural hydrologic cycle, these particles are going to always be minus charged because they got such a low pKa, right? Or which is basically what the isoelectric point of the pH is, that they like to lose that hydrogen ion regardless. Organic matter would be in the same category if it's got carboxylic acid. And then you can look at these non-silicate minerals, iron oxide. They deal with all these are iron oxides all the way down to here, oxy or hydroxides. Here's a titanium mineral, gibbsite we've talked about, corundum's aluminum oxide, periclace's magnesium oxide. You can see here that this category down here, they're always positive because they've got a really high pH for their isoelectric point. And here's some in the middle that can flip back and forth. And these are interesting. We focus on them in soils. And this is why, for instance, goethite, which is the mineral I showed you back here, is important because this is the category of mineral that, depending on the pH in the environment, can flip to either being positively charged or negatively charged. So it can attract different things to its surfaces as a function of changing pH. And here's just another table with some more of these things listed out. You can see these are the clay minerals down here. And the important thing I kind of want to point out about them is that the reason why I said that they always take a negative charge and attract cations onto their surfaces is in part because of this polarity, regardless of the acidity of the environment, that all those terminal hydroxyls like to lose those hydrogens and make minus charges, and then other positive things can stick on to those surfaces. So this is just another depiction of, well, what does it look like at the 0 point of charge? Okay, we can have some mixture of charges on our particle, and it can attract a mixture of cations and anions to its surface. Whereas if we allow the pH to go lower than the 0 point of charge for that particular mineral, the mineral is going to get a positive charge, and in a net sense on it, it's going to attract primarily anions. And in the converse sense, if the pH goes much higher than the 0 point of charge, the particle takes a negative charge and attracts cations too. Okay, so here's an example of some particles in the environment. This is the sum of charges. This is the charge density. And this is pH. Okay. And you can see here, this is a broken axis, meaning it goes up, it's in number of charges per kilogram of clay. And these charges are they're the equivalents, which are moles of charge. So a mole of +1 ions is a mole of charge. A mole of +2 ions is 2 moles of charge, right? And so there's a break in the scale here, because this thing here, if they plotted this out regular, it would be way outside the room. This is one of these clays that's very little altered. This is one that's altered some. This is one that's altered a lot, right? If we think about the sequence, kaolinite, illite, smectite, we go back to this diagram I showed you here, right? Kaolinite's all the way over here. Okay, smectite is in this category here, and illite is here. Smectite is similar to Montmorillonite. And so basically, more stripping, less charge, intermediate charge, high charge. And we see that, on these minerals, how much. It's a big difference in charge, right? There's a factor of, I don't know what it is to go from whatever that, like 2 or 3 up to 72, like factor 30, 35, something like that, difference in the amount of charge. So we can understand this sequence by the substitution in the mineral and the charge density. This difference, this pH effect, shows us that as we as we raise the pH and make the solution more basic, we start to get a little bit more negative charge, right? Because we're forcing a little bit more hydroxides to lose their hydrogen ions. Okay, all of them are bent upward because at high pH they have slightly higher charge. But what defines these clays and their charge is not primarily the acid-base aspect we've been talking about. There's something else that decides not much charge, medium charge, and a lot of charge. And that is ion substitution. So we'll get to that next. But before we get to that, I just want to show you by contrast, this is goethite, that iron oxyhydroxide. See how it doesn't have very much charge either, like kaolinite, but it flips from being positively charged here at relatively low pH, like 4 or 5. And up here at pH 7, it's 0 point of charge, and then it crosses over and it takes a negative charge. So this is one of these minerals that's, again, when we go down a soil column, in addition to seeing variations in organic matter, we'll also see variations in pH. And so we can see the iron oxyhydroxide change from having positive charges to negative charges, depending on where we are in the soil column. Okay, so ion substitution in clays. This is the last thing we'll talk about today, I think. This is what contributes, in addition to the acid-base reaction, to minerals, clay minerals having a high cation exchange capacity. Cation exchange capacity correlates with high sum of negative charges. This is a high CEC, cation exchange capacity clay. This is a moderate cation exchange capacity clay. That's a low cation exchange capacity clay. And how they got there is not so much from the pH effect, but what else the molecules of the clay mineral are made up of to allow it to accumulate charge. And what happens is, you think about those really simple silicon and aluminum sheets in the clay minerals, because the structure of clays are these open flat plates, it's like a stack of tortillas. When we stick another ion in replacement for the silicon or the aluminum, it disrupts the mineral, but not nearly as much as it would disrupt the mineral if we substituted it into like an olivine structure or a quartz structure, which is much more three-dimensional. And so in nature, when minerals are forming, they basically can take other chemical elements and stick them into the matrix of the mineral as a function of things like the temperature and pressure and the composition of the water or the composition of the magma, whatever the mineral is forming from. And so when we get a substitution, we stick in something other than the main thing, we can create a charge imbalance. And the amount of substitution can allow us to have either a low amount or a big amount of charges developing in our mineral structure, which is basically what accounts for these differences. So for instance, within the octahedral layer, remember that's the aluminum layer. So it's based on aluminum ions, which are aluminum +3. we can substitute some other things that are pretty common in the environment that also fit, such as iron 3, iron 2, chromium 3, zinc 2, lithium. Now, interestingly enough, if you take an aluminum in a mineral and you replace it with an iron 3, you don't get any charge imbalance, right? If you put a +3 ion in take a +3 ion out. But if we put a +2 in there, right, then all of a sudden this mineral is expecting a +3, right? But it's got a +2, got a charge imbalance, right? It gives that particle a negative charge, which contributes to it wanting to pull some extra positive charge onto its surface, which is really the gist of this cation exchange capacity. So the development of that cation exchange capacity is the amount of chemical substitution. So we can have substitution by ions into the octahedral sheath. We can also have some substitution in the tetrahedral sheath, the silicon sheath. That is much less common and is mostly limited to aluminum going in instead of silicon. Okay, and it happens, silicon is a +4 ion, so we put aluminum in there, it's a +3, and again, makes a charge imbalance, and this is what gives us the cation exchange capacity of our quartz. Okay, so the next kind of chemical reaction that we want to talk about are reactions that happen on surfaces, ion exchange. Once our clay mineral, for instance, is developed, a charge imbalance because of substitution, it wants to hold stuff onto its surface. And it turns out that what it holds on its surface is a grand competition of a binding coefficient for every single ion that is in solution, wanting to compete for those negative charges on the particle surface, right? And so they each have an equilibrium constant that governs their susceptibility. Some ions may really want to go on. Some ions may be reluctant. And what makes an ion decide to stick onto a particle surface is largely a function, just like when we talked about, previously with the the solubility in water is a function of size and charge. So an ion is really big, where its charge is distributed over a big surface, or really small, where it's distributed over a small surface, may not like the conditions on a particular particle as much as other ions. And we can write equilibrium constants out for this. So for instance, if we have A stuck onto a surface X, X can be anything. It's a B in solution. And then that has an exchange reaction with B stuck onto the solution A out into the environment. So this is A in the solution and B stuck to the middle. That's a chemical exchange reaction. In theory, we could write an equilibrium constant for this exchange, which is basically the proportion of A and B as free ions and A and B stuck to the mineral. In reality, we find out that there's a non-ideality coefficient with this that has a lot to do with how charges are distributed around particle surfaces, which is something we'll talk about next time, as well as the shape and size of the particles, right? Think back to the more charge we have, the more separated the sheets are, right? As I alluded to here. The more separated the sheets are, bigger ions can get their way in, right? And so there's all sorts of factors that determine whether or not a particular ion will stick onto a particle surface or not. They have to do with the combination of kind of chemistry and the physical nature of solids. Nevertheless, we can write equations for this, and we can understand in the broadest sense what population of ions are stuck on any particular solid as a function of these kind of competing exchanges, right? Competing desires for individual ions to be stuck onto particles or be free in solution, and the solution chemistry. So next time we'll start with, I'll show you some examples of, we can take a clay mineral, we can stick it in seawater, or we can stick it in fresh water and pull it out. We can find different ions sticking on there. Any questions about this? So I should have mentioned we've officially started Unit 2. The first, the class is divided into 3 units.